from last time. Like, what is the inverse function? Yeah, those words definitely apply. So the inverse function is what you get if you flip inputs for outputs. So usually when you think about a function, you think about plugging in an input, getting an output value. The inverse function is what you do if you flip that on its head. If you start by saying, what's the output value? Start with the output value and you ask what input value goes to it. There's the idea of an inverse function. And so that means if you actually want to find an inverse function, flip the idea of inputs and outputs, and then do some solving. To find an inverse function, you solve f of y equals x. So you flipped the input and the output for y. And there's like a super short summary of what we've said about inverse functions so far. Maybe with one other observation. Do inverse functions always exist? What's a circumstance when one doesn't? Let's think about the squaring function. Is that the one you're trying to gesture at? Okay. Let's think about, when does f inverse exist? Well, not always. Let's think about f of x equals x squared. To find the inverse, you write down y squared equals x and try to solve that for y. What do you get if you solve that for y? Plus or minus root x. Yeah. And I think you were about to say something further. Oh, okay. Sorry. Then I take back my apology. I did not cut you off. That plus or minus is bad, right? That says that the inverse doesn't send an input to just one output. The inverse wants to send a single input to two different outputs. This is not a function. So that means in this particular case, f inverse of x does not exist. And I think we even kind of see the reason it doesn't exist. The squaring function has the property that it sometimes sends different outputs to the same input. You plug in 5 and minus 5 and square both of those, they each give you 25. So that means that if you want to plug 25 into the inverse function, the output has to be 5 and 25. That's bad. So when do functions have inverses? Functions have inverses when there does not exist two different inputs that both go to the same output. And here's a definition which is that, but now written down. A function f of x is called one-to-one. I'm going to include this word because I might sometimes slip up and say it. Or injective. Which, right, is just a synonym for one-to-one. It means the exact same thing. If you want to use that, then I guess you like your Latin roots a little bit better than your more English-sounding roots. So a function is one-to-one if every two distinct x values result in distinct values for f of x. So a function is one-to-one if whenever you plug in different inputs, you always get different outputs. And let's think about the squaring function. Can you give me two different x values that result in the same output value for this function? What two numbers are you thinking of? 5 and minus 5. That'll do. So let's try x equals 5, which is not equal to negative 5. So here are two distinct inputs. Ooh, I just saw a trip. F of 5 and f of negative 5, are those the same? Yeah. So here's what this means. This function is not one-to-one. Which I'll sometimes also abbreviate as one-to-one. That makes sense? And maybe here's a picture. So here are some functions. I'm not telling you what these functions are. Let's try to answer the question, are these suckers one-to-one? So to answer that question, you need to tell me, are there any two distinct inputs that both go to the same output? And let's look at that first function. Can you tell me two distinct inputs that both go to the same output value? You can be approximate if you have to. Yeah, what inputs are you thinking of? 2.3-ish. That looks like it gives an output value of 2-ish. And did you say negative 0.5? Okay. Negative 0.5. Yeah, that gives an output value of 1-ish. So it sure looks like this has f of 2.3 is exactly the same as f of 0.5. They're both equal to 1. So is that function one-to-one? No. There exists at least two inputs that both go to the same output. Is that the only choice of inputs you could have used? No, there are a bunch, right? I guess like 0 and another place where it crosses the x-axis also walk. I don't have the picture in front of me. So this thing is not one-to-one because of exactly that reason. The second graph, if you take two distinct inputs, are the outputs always distinct? Yeah, I think so. In fact, this is an increasing function. If you have two distinct outputs, then one of them is less than the other. The outputs will be in the same order. So this is one-to-one. And the thing I'm about to draw is just a quicker way to check for exactly that. So let me make a guess as to where you cooked up the numbers 2.3 and negative 0.5. Did you start by thinking about 1? Oh, okay. You could have. Here's one way to check for one-to-oneness. Let's draw this line at y equals 1. Are there multiple places where that graph crosses the line? Each of those three different x values are all x values that result in the same y value. They all result in y equals 1. So here's one way of seeing that it's not one-to-one. So this is not one-to-one since it crosses y equals 1 3 times. In fact, it looks like if you wanted to make up a definition, you might call this like a 3-to-1 function. 3 different inputs all went to the same output. We're not going to make such a definition, but you could. And as a consequence, f inverse of 1 would have to be like 3 different things. Does this have an inverse function? Nope. Let's play the same game over here. There's a line at y equals 1. How many times does it cross the graph? Just the once. Cool. So hopefully that's motivation for the following. The horizontal line test. A function is one-to-one if and only if the graph of the function intersects every horizontal line in at most one point. Does that seem believable? Hopefully the logic has been explained in these examples. If you want to check for one-to-oneness, draw a bunch of horizontal lines. It needs to cross every one of those in at most one point. So like checking just one line isn't good enough because I might have accidentally checked this line. If a function crosses a line in only one point, that's fine. It's not enough to know that it's one-to-one. It needs to be everywhere. Groovy. So that's one way of seeing if an inverse function exists. An inverse function exists if it's one-to-one, which is true if it passes the horizontal line test. So before you should try finding an inverse function, if you have a graph, see if it passes the horizontal line test. If it fails, then you can stop and just say this thing doesn't have an inverse function. So far, so good. All right, let's do one more thing with the graph. I claim that if you have the graph of a function, you also have the graph of the inverse function. That dripping noise is going to drive me absolutely bananas. I don't know if it's bothering you all too. Is it? Can you hear it from where you are? Okay, well that's good anyway. I hope it's not showing up in the recording. Although if it isn't showing up in the recording, then I sound crazy to whoever watches this on YouTube. Oh well. They also think I'm talking to myself in an empty room. So let's play this game. Here's the graph of a function. And let's try to graph its inverse. So first question you should ask. Does an inverse exist? Does that function have an inverse function? Yeah, why?
Passes the horizontal line test.
Yeah, good. Passes the horizontal line test, so it's one-to-one, so it has an inverse. So is this one-to-one? Sure is. Here's what I'm going to try to do. I'm going to try to go from this graph to the graph of the inverse function. I'm going to do so by seeing where the inverse function sends some particular sample points. And let's proceed. So let's start by answering this question. Looking at the original graph, can you find an input value that that graph sends to an output value of 3? Negative 2. People agree? Yeah. There's this point up here at negative 2, 3. So the answer to this question is x equals negative 2. All right. So that means that the original function sends an input of negative 2 to an output of 3. The inverse function is what you get if you swap the role of input and output. So based on that sentence then, what is f inverse of 3? Yeah.
3 negative 2.
You've answered the next question instead of this question. So you've answered like this. You've told me what points on the graph. And we'll talk about that in a second. But what? So f inverse of 3 will just be a number. So what is f inverse of 3? Negative 2. All right. So hopefully nothing fancy there. If you want to know what f inverse of 3 is, that means you want to know what input does the original function send to 3. You can find that by looking at the graph. We found it's negative 2, so that means f inverse of 3 is negative 2. So f inverse sends an input of 3 to an output of 2. So 3, negative 2 is on the graph of the inverse. Let's plot that point. 1, 2, 3, 1, 2. This point is on the graph of the inverse function, 3, negative 2. Think we can play that with some other points? Yeah, maybe we'll talk through one more together, then I'll split you all off to discuss some other ones. So maybe I'll talk about 0. You will talk about 1. You will talk about negative 3. Let's go. So f inverse of 0. So to compute f inverse of 0, I need to figure out what input does f send to 0. So, solve f of x equals 0. What x value gives you f of x equals 0? Yeah, say it out of it. I think you said the right thing. Or you're just yawning. Okay, I called it negative 1 now. People agree with that? Yeah. You say you want f of x to be 0. That means you want a y value here of 0. It looks like negative 1, 0 does the job. That should be a solid dot mod in open circlets on the graph. So f of x equals 0 is solved by x equals negative 1. Yeah, x equals 1. It's to the right of the y-axis, which means it's positive. Yeah. X equals positive 1. Okay. People less convinced that I'm being silly now? Okay. Since x equals 1, an input of 1 goes to an output of 0, inverse functions do the exact opposite. F inverse of positive 1 is then 0. As soon as you know f of an input is an output, you know that f inverse of that output is the input. All right, cool. So that means I know a point that's on the graph of the inverse. I know that 1, 0 is on the graph of y equals f inverse of x. Let's draw that. There's this dripping is really getting to me. Okay. Let's try that again. I know that f sends an input of 1 to an output of 0. Inverse swaps inputs and outputs. So f inverse will send 0 to 1, which is not what I wrote. Now I'll write that. F inverse of 0 is equal to 1. The thing that was the output is now the input. The thing that was the input is now the output. So that means that 0, 1 is on the graph of the inverse function. All right, cool. So I'm struggling enough. So now I'm going to let you answer the remaining two. Tell me, what is f inverse of 1? To do that, find an x value which the original function maps to. Tell me, what is f inverse of negative 3? To do that, find me an input that the original function maps to negative 3. In fact, how many people have already done? Okay, cool, then I'll pause. Give you actual time. Cool. What are we getting? Yeah.
1, -1.
So, putting in context, you told me f, no, not that color, this color. F inverse of 1 is negative 1. Does that agree with everyone on that side? Should I talk through it? Then I will talk. So, whenever you want to know f inverse of 1 equals something, what you are really being asked is f of what equals 1. And let's look at the graph to read that. What do you need to plug into this function to get an output value of 1? Negative 1? because of this point, -1, 1. F of -1 equals 1. Inverse functions swap inputs and outputs. So that means that F inverse of 1 is Gesundheit, -1. So F inverse of 1 is -1. So -1, 1 is on the graph of the inverse function. Inputs and outputs swap. How about the last one? What is F inverse of -3? You've given an answer that includes the right answer, but it's an answer to technically a different question than I was asking. You told me, like, the point on the graph. Yeah. F inverse of -3 is 2, so -3, 2 is on the graph. Should I say that in any more detail? Nice. So, -3, 2 is on the graph, and I want to respect some sort of color coding. -3, +2. All right, and maybe you can believe that if the original function is just a bunch of straight lines, then so will the inverse be. That's not -3, 2. Like, I get that normally I'm not, like, the best with precision, but I wasn't expecting just, like, a steady drip, drip, drip to be so distracting to me. All right. So 3, 2 to -1, 1, and I'm doing this in non-erasable pen for some reason, to 1, 0, to 3, 2. No, I'm still wrong, aren't I? Which of those points is incorrect? So the 32, I think that one was right. You told me that one specifically. I have a point at 32. 0, 1 should be on the graph. I see 0, 1 right there. Well, that's still the problem. It shouldn't be 0. F inverse of 0 is 1.
I think it's supposed to be 1 negative.
Yeah, okay. 1, -1. Okay. Okay. There's a point at x equals 1, y equals -1. There's one of the points. One of the points was at 32. Okay. Where was another one of the points? I don't trust myself at all right now. The purple one. Okay, so 0, 1 is actually right? Okay. And then -3, 2 is right? Okay, cool. There are the points that I now actually believe. Now I'm going to graph this by sketching the straight lines between those. Get a graph that looks something like that. All right. So other than like me falling apart in front of your eyes, that go okay? Nice. So here's the last point to come across on this example. There were like a fair number of logical steps in there. For each point we did a little bit of walk. But ultimately, all we did is we swapped inputs and outputs, because that's all inverses do. But inputs and outputs are something specific in the graph. They're x values and y values. So compare those two graphs. Are those graphs just what you get if you swap all the x values and y values? Nice. Let's write that down. How do you get the graph of f and f inverse? You swap x and y values. If f is a one-to-one function, then the graph of the inverse function is given by swapping x and y values. And maybe I'll say that in one additional way. just because you'll see it written this way sometimes, and it's useful to think of things in terms of symmetries. You can also accomplish this by doing a correct reflection. You can swap all the x and y values by reflecting over the straight line y equals x. And you know what? Let's just verify that that actually works in this particular example. There's the straight line y equals x. Let's see what happens when we reflect some points over that line. If you take negative 1, 1, reflect it over the line, it looks like you wind up over there. Is that a point that I should get on the graph of the inverse? Oh, Jesus Christ. Yeah. There's the point at negative 1, 1. There I've reflected over the line y equals x. Is that a point on the graph of the inverse? Yeah. And it's exactly the point that came from swapping that x value and that y value. So this example is, there are 2 points here. The first point is, if you want to graph the inverse, you just swap all the x and y values. But also the fact that that's not a magic fact. That fact is true because input values and output values are swapped. Neato. Folks feel good? All right. So the next thing that I want to do is I want to remind you that inverses, they're something graphical and analytic. They're the thing we just described graphically. They're also something algebraic. Let's go ahead and algebraically find this inverse function. And maybe I'll give 1 of 2 options here. How many people feel comfortable that they could find this inverse function, that they know what to do? All right. How many people would like me to talk through at least the first couple steps of finding this inverse function? All right. So let's at least set up this problem, and then we'll see how much people want me to do and how much they think they'll do on their own. So I want to find this inverse function. I have an idea of what the inverse to this function means. I want to swap inputs and outputs. So I'll imagine swapping the input and the output, and then I'll do some algebra to solve for the output. So I'll swap inputs and outputs. That will give me y minus 1 over y minus 2 equals x. So I've swapped the x's and y's because y is supposed to be the output. Now let's solve for the output. Solve for y. All right, so there's the step that is translation from asking about the inverse function to algebra. Does that look like an algebra problem that you know how to solve? Maybe I'll see go for a show of hands again to see how much I should do. People want me to at least try talk about the first couple steps in solving this bit of algebra? Okay, seeing no hands, I'll be quiet for a little bit. Tell me what you get. Once you have something you feel confident in, or alternately, if you start doing it and get stuck, raise your hand and I'll come talk to people. Or you can talk to each other too. Today's an excellent day to complain about a particular thing possibly driving me to madness. It's Friday the 13th. That tripping is totally appropriate. have any other solutions? All right, well, let's come together then and maybe start at the start. What seems like a good first step? Yeah. Getting rid of the denominator. Right, so whenever you encounter an algebra problem like this, when you want to solve for a variable, a good first thing to ask is there only one instance of the variable you want to solve for? In this case, the answer is no. When there is just one instance of the thing you want to solve for, you can imagine undoing things one at a time, and then eventually you'll solve for y. But you can't do that here. Instead, you ask yourself, what's the most annoying thing there? Division. But you know how to undo division. Multiplication undoes division. Let's multiply both sides by the denominator. And that will be y minus 2. So I'll multiply both sides by y minus 2. All right. And the whole point of doing that is those y minus 2's cancel. All right, great. Now there is no division left. I would say that improves our life. What next? Yeah.
Multiply x through.
Yeah. Let's multiply the x through. And all right, what's the motivation for that? Eventually we want to get like the y's on their own. So it's annoying that I've got one of those y's stuck inside some parentheses. Let's get that y out of the parentheses. Distribution does that. Xy minus 2x equals y minus 1. Neato. So far, does that agree with what people did? All right. What next? So I want to get like y on its own. That's my goal. If I could get all the y's reasonably simply looking on the same side, that would help. What could you do to get all the y's onto the same side here? Yeah.
Subtract the xy over and add the 1 on the other side.
I hear I subtract xy from both sides and add 1 to both sides. Let's write that down. Let's subtract xy from both sides, add 1 to both sides. How many people instead would have liked to subtract y from both sides and add 2x to both sides? Would that accomplish the same goal of getting all the y's onto the same side? Yeah, so it'd be totally correct to do that. And if you do it, you'll wind up with a very mildly different looking answer. All right, so let's do that. So we add 1 to both sides. That cancels with these ones. We subtract xy from both sides. That cancels those. We wind up with y minus xy equals negative 2x plus 1. Seem okay? And all the y's are at least now on the same side. So let's look at the side that actually has the y. Do you see anything that factors out of that side? What factors out if you factor out? Yeah, a y. So let's factor a y out of that side. And that's good. We want to isolate the y. If we do that, then y is pretty close to being isolated. It's a single factor on the one side. So let's see, I guess we get y 1 minus x equals, well, that's the same as 1 minus 2x on that side. So far, so good? What next? Yeah.
Divide the 1 minus x over.
Divide 1 minus x to the other side. And that's a reasonable thing to do. I see only one y on the one side. So just undo whatever is done to that y. I know what undoes multiplication. Division undoes it. y equals 1 minus 2x over 1 minus x. Did anyone get a slightly different looking answer than that when they walked this out on their own? What'd you get?
2x minus 1 over x.
Excellent. That's exactly the answer I wanted to hear. Those two are exactly the same function. In fact, does anyone already see that? Yeah, why? Yeah, so if this numerator is exactly negative that numerator, this denominator is exactly the negative of that denominator. Can I multiply the numerator and denominator by -1 and not change the thing? So those are the same. They look different, but they're the same. All right, so we have the inverse function. Could we use the graph to check this? Yeah, let's graph the original function. Happily, I've already pulled up that graph. And I know what the graph of the inverse function should look like. The inverse function should be what you get if you swap the x's and y's. And Desmos lets you just do that. If that's f of x, Desmos will let you graph x equals f of y. So there's what the graph of the inverse should look like. Let's graph the function that we have and see if it does the job. Let's graph 2x minus 1, not 11, divided by x minus 1. Does that look about the same as the purple thing? And maybe just for the sake of completeness, let's also do that one. 1 minus 2x divided by 1 minus x. Is that the same thing again? Nice. So all of those, the same function. So that's just the reminder that you can find inverse functions algebraically, and that you can check them by looking at a graph. The next thing I want to point out, and maybe I'll accelerate myself a little bit because I have 14 minutes. Let's think about domains and ranges. So let's suppose I ask you to find the domain of an inverse function. Let's think about what the domain of a thing means in terms of a graph. So I'm going to write this out in a few steps. Domain of f inverse of x. How do you get the domain if you look at a graph? I want to do everything in terms of graphs right now. It's all the x values on the graph. So the domain of f inverse is all x values on the graph of f inverse. X values on the graph of the inverse function. What does taking the inverse function do to x, y values? Swaps it, right? X values become y values. This is the same as all of the y values on the graph of the original function f. This is the same as all y values on the graph of f. Do you agree with that? Ooh, but what's the magic word that tells you all of the y values on the graph of the function? The range. So here's the whole point of this line. The domain of an inverse function is the same as the range of the original function. The domain of a function of an inverse is the same as the range of the original. Could I swap the domains and ranges there? What's the range of the inverse function? Domain of the original. And let's check that in this example. So there is a function and its inverse. Let's focus on just the function. Let's think about the domain of that function. What's the only thing not in that domain? 2. Because if you plug in 2, you divide by 0. It's also the location of the particle asymptote. Either graphically or algebraically, depending on what you like. There's the graph of the inverse function. What's the only thing that that graph does not hit? 2. This function happens to have the property that it never attains its horizontal asymptote. So this fact holds up. The domain of the original is the range of the inverse. Let's check the opposite. What's the only thing not in the domain of the inverse function? What's the only thing not in the domain of that? 1? Is that the same thing as the only thing not in the range of the original? Awesome. This check holds up. Domain and range actually swapped. So the last thing I want to do in this packet is the following. I want to wax a little bit technical. So right now we have like a strategy to find an inverse function. If you want to find an inverse function, you solve that for y. But that's not what the inverse function is. The inverse function is the function that undoes the original function and is undone by. So that means for any function f, the inverse is the unique function satisfying these two conditions. F inverse of f of x is always equal to x. F of f inverse of x is always equal to x. So really the definition of the inverse function is that some compositions simplify down to just x. So if someone hands you a function and they say, here's a function, here's something that I believe is the inverse, and you want to verify it, you just need to check these compositions are both x. And let's see that in practice for one example. Let's think about the example we just found. 2x minus 1. We just checked that the inverse function to x minus 1 over x minus 2 is 2x minus 1 over x minus 1. I believe I wrote that down correctly. 2x minus 1, x minus 1. Yeah, cool. In order to check that this really is the inverse function, I need to check two things. I need to know that f of f inverse of x is equal to x. I also need to know that f inverse of f of x is equal to x. And maybe it's a bit of motivation. In the homework poster for today, I'm asking you to do exactly this. In fact, for this very example, I think. So, in order to check that this is actually the inverse, I need to do those two things. Do you think it's going to be similar work to do one as to do the other? Probably. F and f inverse are really similar looking functions. They have the same flavor of function. Well, let's try to do one of these two checks. I think I have enough time to do one, but not the other. Should we together do the check for 1? For 2? I think the ones have it, but it's like the same work for either one, right? So it's kind of an irrelevant question which one would be lost. So let's do 1. So to do that, I need to evaluate f of f inverse of x. And most of the work here is remembering how to compose functions. Do I have a formula for f of x? Yeah, it's like up there somewhere. Let's use that formula. That is x minus 1, so blank minus 1, divided by blank minus 2. And what do I want to put in those blanks? Well, f of x. Because, like, f inverse of x. This is the thing I want to put in those spaces. Do I also already have a formula for f inverse of x? Sure do. Let's use that. This is the same as 2x minus 1 over x minus 1 minus 1 all over 2x minus 1 over x minus 1 minus 2. Did I plug those in correctly? Cool. So, as I said, like most of the work I'm doing this problem is just writing down the inverse function. And now the job is simplifying. And I know what it must simplify down to. I know for a fact that it should simplify down to x, because I really believe this is actually the inverse function. The graph told me the domain and range were lined up correctly. I found it by doing algebra. All the things point to it being right. If I want to check this, I just need to do some algebra to simplify. If you saw this and were told to simplify, what would you want to do?
Common denominators for the -2 and -1.
Yeah. In the numerator itself, I see a fraction minus 1. It's annoying that it's not just one fraction, it's annoying that it's a fraction minus 1. Let's get a common denominator so I can subtract those fractions. Do the same in the opposites. Yeah, do that twice. If we do that, we will get 2x minus 1 over x minus 1 minus x minus 1 over x minus 1. Because all this is just 1. All over 2x minus 1 over x minus 1 minus 2x minus 2 over x minus 1. Because all this is just 2. Folks feel good so far? All right. So we have common denominators. What's the whole point of getting common denominators? What does that let us do?
Do the subtraction.
Yeah. Subtracting fractions is now easy. So I get a common denominator. Let's subtract some fractions. This becomes 2x minus 1 minus, and being careful with parentheses because I need to subtract all of x minus 1. All that divided by x minus 1. All over 2x minus 1 minus 2x minus 2. All over x minus 1. I have those fractions correctly? Or subtract, as it were? Whenever they have, you add or subtract fractions with a common denominator, they both just get the same denominator, and you add or subtract them. All right, let's keep on simplifying. What do you notice here that you can use to simplify? I've got 1 minute. Both the numerator and denominator are divided by the same thing, right? If you divide the numerator by 5 and the denominator by 5, you don't do anything. So let's just cancel those. Those cancel. And in fact, all that 2x minus 1 minus x minus 1, what is that? Just x. People agree? Cool. All the stuff in the denominator, what is it? Write it out if you got it. Better be 1. People agree? Oh, I wrote 2, but I said x at least. What's x over 1? Is that exactly what I needed to get? Think you could do the same thing again for the other one? All right. Then your open-ended homework assigned today is basically done. On Monday when we meet, we will start talking about exponential functions.